So far, we assume that effects from predictors, it's just additive effects. So the predictors do not influence the effect of each other. But this is not always the case. And although predictors are not correlated, they still can influence the effect of each other, and this is what we call interactions. You can actually account for interaction effects in ANOVA model and in a regression model. So let me show you what exactly it is and how to account for this effect. Well, two predictors interact when effect of one predictor depends on the value of the second one. Let me show you a couple of examples. So let's say that we have a model which compares salaries of different persons, also males and females. So in this case, I have x1 and x2 as qualitative factors, right? So I took this data from these sources, and I took it in 2021. Okay. So this is the data set. So that's the average net salary in Italy. This is average net salary in Denmark. It's euro a month. This is average net salary of all females in these two countries, and this is average net salary of males. Okay. Now I can show the effect. I can, of course, make a regression model, but I can show the effect, the slope of every factor as follows, right? So this is males, this is females, this is salary. So the difference between males and females, you remember that in this case it will be, I think I should swap it vice versa. Sorry about this mistake. So this should be males and this should be females, right? You can see that 2663 minus 3003. So this is effect from males and females. So it's a slope of this line. And then you can see the difference between Italy and Denmark. It's quite large, and this is the slope of this line. So these are the effects of the every variable of country and of gender. If I make a model, the slope of these lines will be my regression coefficients. Okay. Now, let me now make a split. So now I know also from the same source how many euro per month a month males in Italy earn, females in Italy, males in Denmark, and females in Denmark. And now I can show you the effect from gender. In this case, it's right, females and males. You can see that this is Denmark, this is Italy, and this is average. This is average main effect, right? So the main effect is 340. So it means that males earn by 340 more than females. In Italy, this effect is 90, but in Denmark, it's 590. So it means that effect from gender depends which country you measure this effect. So effect from one variable depends on the value of the second variable. So effect from gender depends on effect on the value of country. And that's exactly what interaction is. When effect of one variable depends on the value of the other variable. Okay. So in this case, we can say that country changes the effect of gender by plus minus 250 euro. And that's what we call synergistic interaction when you increase or decrease, but the magnitude is the sign is the same. Okay. Let me show you now the more numeric example. So in this case, I have a chemical reaction. It's a production of hydrogen gas. This is the reaction, right? And then I can add a catalyst in order to make this reaction more efficient. And usually the catalyst, it's a copper sulfate, which is used as a catalyst. I would like to estimate effect from the catalyst. I would like to estimate also effect from the reaction time. So you can see I have two variables. The first, it's a reaction time in seconds, and I use 5 seconds and 10 seconds. The second, it's catalyst. It's just a dummy variable, yes or no, 0 and 1. And then the y, it's a volume of produced gas in cubic centimeters. Again, you can see the effect from the time as these two lines. So this is what I got when I had no catalyst in the system. And this is what I got when I had a catalyst in the system. So apparently, the reaction is faster when you have a catalyst in the system. But it means that presence of catalyst changes effect from time. Again, this is exactly what we call interaction. When changing value for one variable changes the effect on y for the other variable, for the second variable in this case. Okay. Let me compute the interaction effect, right? So here, it's the blue line. It's when we have no catalyst, right? So this is the value for time, so 10 and 5, right? So the distance is 5, right? So this is delta x. Yeah? The delta y, it's 20 minus 10, so it's 10. So this is delta y. This is delta x, and this is the slope, right? So this is the regression coefficient I get for the variable for the time when there is no catalyst in the system. Now I can do the same when there is a catalyst. So the delta x, it's still 10 minus 5, and delta y will be 60 minus 30, right? So this is delta y. This is delta x, and the slope, it's a ratio of these two deltas, and this is 6. You can see this is B1 if you have a catalyst, and this is B1 if you don't have a catalyst. So adding catalyst changes coefficient for the time, right? So it makes slope like 3 times larger, or by 4 centimeters, cubic centimeters per second larger, right? So this is exactly the interaction effect. So this is interaction between the catalyst and time. Okay. How to account for interaction effect? Well, in R, you simply add additional term. You can see I get back to my income H example. So this is H region. This is exactly what we had before. But now you can see I added a new term, right? H colon region. And that's exactly how to do how to account for interaction. Also the same in ANOVA. You can also do it in ANOVA. Let's see the difference, right? So this is the new table. Now I have H effect. I have region effect. In this case, I use mean-centered data for H. So that's why the intercept is significant. But for region, I use the dummified variable. So it's 0 and 1, right? Now look, this is the interaction effect. So it's not significant. So it's probably not reproducible. But in our data, we have interaction effect, minus 84. So let me explain the meaning of this minus 84. How to explain it? Well, to explain it, let's make these two separate models. First, I make a model where income depends on H, but look, I use a subset of my D where region equal to 0, right? So I use only subset of my D when the region is Scandinavian region, right? So this is effect of H in Scandinavia, right? This is effect of H in Mediterranean region. So you can see in Scandinavia, you have a larger growth of salary with H. And how big the difference is? Well, let me visualize it first. So these are all Scandinavians, these are all Mediterraneans. You can see that region has its own effect because these lines are distanced, right? These lines are distanced. This is just effect from region. But you can also see that the slope of this line and the slope of this line, they are a little bit different. It's barely can see it, but they are a little bit different. For example, look at this distance and at this distance. It's a bit larger, right? So the difference in slope, it's exactly the interaction effect. And we can compute the difference in slope, right? It's 869.5 minus 785, or vice versa, actually. And that's exactly, not exactly because I have a little bit some rounding problems here, but you can see it's the same value by if you round it up to the whole number. So it's 84. So the slope of line, which shows you how income depends on H, in one country is a little bit larger than the other country, right? So also its effect from H, it depends which country you're from. So it depends on the value of the other variable, and that's exactly the interaction. How interaction influences your model? Well, it makes it less linear. So you can see that, I know it's probably difficult to see it on this plot because in this case, it's difficult to see that this is not a plane anymore, it's a surface. But if I make a counterplot, you can see it clearly because now instead of parallel lines, you have a kind of curves. Why curves? I'll show you in a minute because I have a dedicated raster app for that to show you that. But so far you can probably spot it here, and this is just another plot. Probably you can spot it a little bit better here, that you have actually not parallel lines, but you have some curves. Okay. So when you have interaction, then if you account for interaction term, then your counterplot will look a little bit curved. Okay. So this is just a summary. And of course, you can have interaction if you have more than 2 predictors. For example, if you have 3 predictors, this is without interactions, and then you can account for all pairwise interactions, right? So in this case, you have 3 possible interactions. And of course, it will require more data points because the more regression coefficients you need to estimate, the more data points you need. You remember that you need at least by 1 more data point, but in fact, you need more because you also need to estimate residual. So let's say 3, 5 more data points than the number of regression coefficients, okay? You don't need to account for 3-factor interactions or 4-factor interactions. Usually it's just noise. It's just random, but accounting for two-factor interactions can be a good idea. So now, please watch the video about Grasta app that explains the multiple linear regression model. It also has an interaction term. You will see it in this video. So first watch this introductory video, and then I highly recommend you to play with this app because it makes understanding of MLR model much better, especially interaction. And then come back for conclusions and how to do things in R.